welcome to another Physics QBits video. In this video, we're going to go over how to calculate electric fields in systems that have multiple point charges, and we'll do one quick example to show off how this works in one dimension. If you feel like you don't have a great conceptual understanding of what an electric field is, I'll encourage you to check out the last Physics QBit video we had, which talks about kind of conceptually what electric fields are. But without further ado, let's hop right into this video. So before we do our example problem, I wanted to very quickly review kind of some of the formulas involved when we're dealing with electric fields. And so remember, electric fields are vector fields that are given by the following equation. The electric field E is given by K Q source over R squared. Electric fields are created by source charges, right? Every time you put a charged object in space, it's going to create a local electric field. And so this Q source is the charge of the source charge. So this is the source charge, and this is the thing that's sourcing the electric field, right? This K here is just Coulomb's constant, so it's just got a value of 9 times 10 to the 9th in whatever units. I forget the exact units, but you can look these up if you're interested. And this R value, this is the distance from the source charge to the observation point in the field that we're looking at. So this is the distance from Q source to field location. And so we also figured out that positive and negative source charges produce electric fields in different directions, right? When it comes to thinking about the directions of the electric field, we always consider a positive test charge. And so if we have a positive source charge and a little positive test charge, these are going to be repulsive against each other, right? And so that means the source charge points away from positive Q source, and if we have a negative source charge, right, that's going to create an attractive field because it's going to have an attractive force when we put in a positive test charge. And so we know that the electric field lines must point towards negative Q sources. Okay. As far as the physical meaning of the electric field goes, we can kind of inspect the definition of Coulomb's law and figure out what the electric field actually means. So taking a look at Coulomb's law here, the electric force between 2 point charges is K Q1 Q2 over R squared, but we can kind of factor out Q2 so that it's just multiplying this kind of first term here. And we recognize that this guy here is the electric field, right? This left-hand side term. And so we can kind of write a more compressed version of Coulomb's law by thinking about the electric field sourced by one of the charges multiplied by the test charge, which we treat kind of the other charge in this interaction as a test charge here, right? And so we can see that the structure of this equation tells us that the electric field tells us how much electric force we get per unit test charge we plug in. In other words, the units of the electric field are newtons per coulomb. And if you multiply by a test charge, then you can kind of figure out proportionally how much force you get per unit test charge you plug in here. And finally, at the very bottom, I've left a couple of cartoons just kind of showing what graphically these electric fields look like nearby both positive and negative charges. Like we alluded to before, positive charges have kind of outwards pointing repulsive fields, whereas negative charges are going to have inwards pointing attractive electric fields. Okay, so so far we've only talked about what happens if you have an electric field from kind of one source charge at a time. And so one useful question to ask is what happens if you have multiple source charges, right? How do you compute the kind of total electric field? Well, it turns out the superposition principle is really useful here. The superposition principle states that the total effect of having multiple electric fields at a particular point is simply the vector sum. In other words, the total electric field is just the sum of all the kind of individual electric fields from all the individual point charges. And so let's imagine we have like a position here, and this is our kind of field observation point that we're interested in understanding the electric field at. And in order to figure out the total electric field, we have to draw the 2 individual electric fields and then do the vector sum. And so in this kind of illustrative, very schematic, hand-wavy example, the electric field from Q1, this red positive charge, like we said before, is going to be a repulsive field, right? And so it's going to point kind of along this direction, the sort of line of sight between Q1 and the field observation point. And it's going to look something like this. So let's label this guy E1. We also know that Q2 is going to produce an attractive field, right, because it's a negative charge. And so Q2 must kind of create an electric field that looks like this. Let me draw the guideline really quick. Perfect. And so the electric field from Q2 is going to be attractive, pointing towards the negative charge. So this is going to be what E2 looks like. And so the idea is if we want to find the total electric field, the superposition principle tells us it's just the sum of these two, the vector sum of these two vectors here, right? So what I'm going to do is kind of draw a copy of E2 that looks something like this. And this way I can draw it so that it's kind of appended to E1 in the way that we normally do vector addition, right? And the total vector, E1 plus E2, is given by the vector that spans the initial position from E1 out to the kind of end of E2, the last vector in our little chain. And so in this case, this is our total vector, or our total electric field vector created by the combination of both E1 and E2 by superposition. All right, so I think conceptually this is easy enough, and so I wanted to hop into a very quick example just to show off kind of how we use this superposition principle in calculations. So in this example problem, we're going to be doing a simple one-dimensional electric field problem. If you're looking for a more complicated example, you can check out the office hours video linked in the description where we work on a more complicated 2D problem. I just wanted to keep this one kind of simple so we don't spend too much time on algebra here. So for this one-dimensional problem, we have a number line marked with positions in centimeters. We also have a positive 3 nanocoulomb charge drawn here in red and a negative 8 nanocoulomb charge. Reminder that nanocoulomb is 10 to the minus 9 coulombs here, so it's a billionth of a coulomb. We want to use the principle of superposition to find the electric field vector, the sort of combined electric field vector, I should say, at this marked position at 3 centimeters. So this one right here. And so to start this problem, I think the easiest thing to do is to make a quick sketch of the two individual electric fields like we did on the last page, just so we can kind of visually see what's going on. And so first we can recognize that the positive charge here, this red charge, is going to produce a repulsive electric field at the marked position, right? And so that means that the electric field from the first charge, which we'll call E1, points to the right, like this, in red. We can also see that we have a negative charge, and so the negative charge is going to produce an attractive electric field. So it's going to point, the electric field, I should say, is pointing to the left, and we'll call this E2. And by the superposition principle, right, the total field is going to be the vector sum of these two guys. And so because they point in opposite directions, we should kind of expect that they'll cancel each other out mostly, or at least partially. Let's see how this works kind of with the magnitudes as well. So algebraically, let's start by trying to compute the electric field from the first charge, E1, right? So we know that the electric field is given by K, Q1 over R1 squared, where Q1 is going to be the charge of the object that's producing this electric field, in other words, 3 nanocoulombs, right? And R1 is going to be the distance between this red charge, okay, and the field observation point here. And so we can count the little tick marks, and we can find out that there are 1, 2, 3, 4 centimeters, okay, between the charge and the field observation point. So plugging in our numbers, we can use Coulomb's constant, 9 times 10. So plugging in our numbers, we can use Coulomb's constant for K, 9 times 10 to the 9, times 3 nanocoulomb charge, so 3 times 10 to the minus 9 coulombs, over the distance squared, which we figured out was 4 centimeters. So I'm going to do 0.04 squared because everything we plug into this equation should be in kilograms, meters, seconds, coulombs, etc., etc. And so when I plug these into a calculator, I find out that the magnitude of E1 is going to be 16,875 newtons per coulomb. And I'll write even a little plus sign to remind ourselves that it's pointing to the right, okay? We can also apply Coulomb's law to the second charge, so we can think about computing E2. And we know E2 is going to be K Q2 over R2 squared. And so if I identically plug in the numbers here, I'm going to get 9 times 10 to the 9th for Coulomb's constant. I'm going to have a charge of 8 times 10 to the minus 9 coulombs. And, the distance between the field point and the source charge is now going to be a total of 6 centimeters. So we have 0.06 squared. If If I plug these guys into a calculator, I will find that we have a 20,000 Newton per Coulomb field from the blue charge, okay? And in this case, this field points to the left, so we can even stick a negative sign here. Actually, I'm not even going to stick a negative sign here. Let's just talk about the magnitudes. Maybe a little bit lazy here. And so the reason is I want to point out kind of something important here. You'll notice that when we plugged in the charge, okay, we plugged in the absolute value of the charge. We just plugged in the magnitude, right? 8 times 10 to the minus 9. We neglected this sort of minus sign that's associated with the fact that this is a negative charge. The reason we can do that is because when we're thinking about just the magnitude of the electric field, right, it doesn't matter whether the charge is positive or negative, the magnitude is the same. The negative only matters when we're thinking about the direction, okay? Because we've diagrammed our electric field vector already to be leftwards, we're already being careful about the direction, and so it's totally safe to plug in just the kind of positive values here, the absolute values, and then later on when we're doing our vector sum, as long as we're careful to remember that this electric field points to the left and therefore is kind of a negative value, right, then we're okay. We don't need to plug in this negative 8 nanocoulomb charge. Now that we have both of our constituent electric fields, right, we can see that by this principle of superposition, the total electric field must simply be the vector sum of these two individual fields. So E1 vector plus E2 vector. Okay, because we're in one dimension, keeping track of the directions is really easy. Positive values point to the right and negative values point to the left. And so because E1 is rightwards, we know that the vector E1 can be represented with just a positive 16,875, okay? And because E2 is pointing to the left, when we add this vector, we're really subtracting the value of the magnitude of E2. And so we have a minus 20,000 newtons per coulomb from E2 here. And so if we do this arithmetic problem, we find that the total result is that the electric field is a minus 3,125 newtons per coulomb. Because we see a negative sign here, right, this means that the leftwards pointing value was greater than the rightwards pointing value, or in other words, the kind of total electric field at the very end points to the left. And so if we wanted to diagram the total electric field, it would look something like that. Okay, and so now by superposition, we have figured out what the total electric field is from these two kind of constituent individual electric fields. So there's really not that much more I want to say about this problem other than pointing out the key idea here that the electric field is a vector quantity, right? So make sure that when you're doing this vector sum that we did down here, okay, that you're careful about inserting the negatives and positive signs for rightwards and leftwards pointing vectors, okay? So just be careful about this sort of vector quantity thing. Other than that, I'll scroll back and leave us with the principle of superposition slide, just so we can kind of look at the general rule, and we can call it a video. So if you have any thoughts or questions about the principle of superposition, you can feel free to leave those in the comment section down below. If you're looking for a more complicated problem, like I said before, we'll do a more complicated example in the office hours video. I also want to take a second to advertise that I do private tutoring online, so if you're looking for more specific one-on-one help, you can feel free to contact me with an inquiry at the email in the description below. And finally, as per usual, please don't forget to like this video and subscribe for more free physics problem-solving tips and tricks. It really helps. In any case, this has been Physics Tutoring Quantized.